I welcome you all to the class on forming operations. So we have covered already rolling. We will in this class we will be covering basically the wire drawing, tube drawing, extrusion and forging operations. So let us start with wire drawing. So wire drawing in wire drawing what is done basically that a rod is into a wire, right? So this is the wire and this is a rod. This rod is having diameter d0 and is deformed into d1. Okay, so this is generally a cold working process. As you know, cold working is below recrystallization temperature. So any forming operation which is carried out below recrystallization temperature is known as cold working process. So here we use generally stationary dies. As we have seen in the rolling operation, we have used rollers. Here we are going to use dies. They are made up of very hard materials, right? The surface of this one is very hard. Okay, so this die is used, and through this die a portion of the metal, this one is pulled out, right? So when it is pulled out, then this deforms, this rod gets deformed and we get the wire. So this is how the things are done. So as you can see, there are many things in this one. This is the drawing force, which is sigma 2, and there are 4 zones. Z1 is zone 1, zone 2, zone 3 and zone 4. So Z1 is zone 1, which is known as deformation zone. This one is entry zone. Z2 is entry zone. This one is exit zone. Okay, so let us see, and 2 alpha is the die angle, the angle by which this whole metal is getting deformed, right? So let's see about the deformation zone, that is zone 1. So in zone 1 the deformation happens, whatever deformation which is going to happen, that happens in deformation zone. Okay, so 2 alpha is the die angle, that is the angle of deformation zone, right? So this angle is subtend here at this point. So this is 2 alpha. So if you just make it half, it will be alpha. So 2 alpha angle varies from 12 degree to 48 degree, where why this 12 to 48? Because 12 degree is used for hard materials and 48 degree is for soft materials. Now why 12 degree for hard materials? So as you can see here, if it is 48 degree, it will be here. If it is 12 degree, it will be somewhere here like this, right? So this is 12 degree. So what kind of thing are you able to see? If this is 12 degree, that means very less deformation is like as you can see that the deformation rate is very less. As you can see here, this thickness is reduced to this thickness. D2 to D0 to D1 has been covered, or you can say has been achieved within the length L. But if you, the 2 alpha or die angle is 12 degree, then D0 to D1 is achieved in this length up to here. So to achieve the same diameter in both the cases, it has to travel a long distance. That means the deformation rate is very small in case of 12 degree, and that is required because as hard materials, they are brittle little bit, and it is very difficult that to deform them, and that's why the deformation is done very slow. But soft material, it is easy to give high deformation, and that's why the angle is given 48 degree. L, what is L? L is the length of deformation zone. It is also known as die land. So this length as you can see Z1 from here to here, this is the length L. Okay, so there will be friction, as we have seen in the rolling operation, in between the roller and the surface of the object there was a friction. Similarly in this case also there is a friction in between the roller, in between the die. This is the die surface and this is the material surface, so in between these two there will be a friction here. So if we can say this one is this uh, angle is mu1 and this is mu2 here. It may be different, so I have taken mu1 and mu2, right? So in between this both the surfaces it is mu1 coefficient of friction and here it is mu2. So next zone is about the entry zone, and that is also known as lubricating zone, because the lubrication, that is the liquid which is poured, is liquid that is poured in this zone only, right? So this zone is also known as entry zone. So here there will be almost no friction, okay, and the lubrication is applied in this zone, from this zone only. So the lubricating liquid will enter through entry zone and it will go along with the metal up to here, it will come, okay, and it will come here and it will get collected at this point. The lubricating liquid will be collected at exit zone. So based on this lubrication, there are three types of wire drawing possible. One is no lubricant condition, another one is liquid lubricant condition, and one is solid lubricant condition. So in case of no lubricant condition, when we don't use any lubricant, so what happens that due to the large deformation, there will be you can say large amount of heat is liberated. Friction, due to more friction and more deformation, large amount of heat is generated, and that heat basically hampers the surface of the wire which is coming, and that means the surface becomes burnt. Actually the color will be burnt color. Liquid, if we use liquid, then what happens, because of the liquid which is used, the surface becomes very dull, okay. So some of the liquid lubricants are kerosene, vegetable oils and mineral oils, which is very easily available, but the best one is solid lubricant, because uh, when they are used, the surface which we get is bright shining surface, okay. So here solid lubricants are carbon powder, graphite powder generally, and glass powder sometimes. Now zone 3 is known as sizing zone. I'll tell you why it is sizing zone, because it since as you can see here, it is a constant zone, from here constant diameter zone, and it is a little bit longer. Why it is kept longer? Why not directly we can exit here? Why we have to travel up to here and then we have to exit? We can directly have an exit zone at this point only, but we don't go for that. We rather we travel this much distance. Why it is so? And it is written 2 to 5 meter, 2 to 5 meter. You understand how much long it will be and why it is so? Why this sizing zone is required? Because you see it is written that this is used for converting elastic deformation present in the plastic deformation zone into total plastic deformation. What is the meaning of this one? Look at this. As you know about the stress strain curve, this is sigma, this is epsilon, this is stress, this is strain, and if we take mild steel rod which is converted into a steel in a wire, so mild steel have this kind of curve, a stress strain curve. Let's suppose that a material which is deformed up to here, okay, and then they are left. What will happen? They will come back. Actually a stress we are releasing, So they will be coming back and they will come here and it will finish. So this is known as plastic deformation, and this one is elastic deformation, which is like earlier the total deformation is this much, but finally when you remove complete pressure which is applied, then you find that the deformation, total deformation has decreased. So this is known as elastic deformation. So generally when they are coming back, they don't follow this path, rather they follow another path parallel to this line, right? So they will be parallel to this line. So they will cut here, and this is known as plastic deformation. That means this will be the permanent deformation. So let's suppose this is the rod, and if it is pulled, right? So you will see that when it is pulled, then it has reached to here, this much length, let's suppose, right? But as soon as this one is removed, this force which is applied, let's suppose this is the force F and this is F, then what we get, this much length. This is the final length. Why this happened? Why not it remain like this one? Because there is a certain elastic deformation also included. Okay, so elastic deformation means as soon as the applied load is removed, then elastic deformation will be, it will disappear, right? So that is what happens in case of this one. So understood? So that is if we want that this elastic deformation converts into plastic deformation, then we need to keep it for some time. We need to maintain that pressure for a longer time. As much long you will put, that much deformation is elastic deformation will convert into plastic deformation. Okay, so this point is clear. Now what about exit zone? So this is very long, as it is written 2 to 5 meter. Exit zone, it is a safety zone used for safeguarding the equipment and manpower due to high pressure and high temperature lubricants. So when the wire which is coming out, obviously with that lubricants will be coming out, and there is a chance that that lubricant will be very very hot and it may come to the workers and all those. So that's why exit zone is prepared properly and safety things are kept. Okay, safety measures are taken. Okay, so this is if the lubricants are not used in the wire drawing operation, no divergent zone is required. So as you can see that divergent zone, so here is the divergent zone. So if there is no lubricant, then no divergent zone is required in the case of wire. So if we see, there is a term known as draft. You have to know draft. Question may always ask what is the draft. That is also known as coefficient of elongation. Coefficient of elongation or draft. Draft को K से denote करेंगे. That is A0 by A1. This is initial by final. That is initial area, cross-sectional area divided by final cross-sectional area. Okay, so that we have to remember. Another thing is drawing a stress. How much stress will be generated? That is sigma 2. You have seen that is the pulling force right here in the diagram. This is the sigma 2. So what is the formula for this one? Sigma 2 is equal to sigma by, what is that sigma by? Here is the sigma y, this one is the sigma y. This is the yield stress, that is the strength of the material. See, below this one is elastic zone and this is plastic zone, right? So you have to remember, yield stress is the zone after which plastic deformation starts. Below that, if you are applying any kind of pressure, then there will not be any plastic deformation. That means whatever force you are applying, that will be uh, like as soon as the force is removed, immediately the job will acquire its original shape. So that is the sigma y, and there is a term 1 plus b upon b, okay, and there is this one in a1 final by initial. So where b is basically it is mu upon tan alpha, mu upon tan alpha or mu cot alpha, we can write it, okay. Mu, you know what is mu? Mu is the coefficient of friction. I told, mu is the coefficient of friction, and that has been taken as equal on both the surfaces, right? And what is alpha? Alpha is half of the angle, half of diangle, and mu is coefficient of friction. So this is the stress. What about load? So drawing load, will be that is equal to sigma 2 into how much? A naught or A1? What do you suggest? What we should write, A1 or A naught? Look at this diagram. Okay, this is the A1, sorry, this is A naught and this is A1. Now you tell me what will be the drawing load? It will be sigma 2 into A naught or A1? Yes, obviously this is sigma 2 into A1, because the force is applied in this, it is pulled, isn't it? It is not pushed from this side, it is pulled. So the force is applied on this surface, so load will be pressure into area, right? So that will be A1. So be careful about this one. Okay, so this is all the things. The above is calculated without considering the horizontal component of frictional force acting in the backward direction. Okay, so obviously the forces which are acting, it is not only perpendicular, there is a horizontal friction component, and if we add, then it will be little bit more complicated. So just leave it, and we'll talk about how much maximum reduction is possible. So maximum reduction possible, when, how much is the maximum reduction possible? Yes, so the drawing a stress, it becomes equal to sigma y. Okay, that means that as you can see one thing, 1 second, look at this expression. This is 1 by b plus 1. That means if b increases, sigma 2 is going to decrease. If b increases, sigma 2 is going to decrease, right? That means if b, what about b? Okay, so b increases. So b can increase in what sense? In what way it will increase? Either mu will increase or tan alpha will decrease. So tan alpha will decrease means alpha will decrease, right? So so maximum reduction, one thing, yeah. So mu, if it increases, sigma 2 is decreasing, right? Increasing, b is increasing, and due to b increment in b, sigma 2 is decreasing. friction is increasing, so the drawing stress is decreasing. It's a little bit confusing, isn't it? If friction is increasing, then drawing load is increasing. How is it possible? Some issue? Okay. Okay, I'll talk about this one later. Let us see here. First of all, actually, take one ideal condition. Take the condition that is mu is equal to 0 and b is equal to also 0. In that case, what happens? That sigma 2 becomes sigma by into ln. Now this is initial upon final, that is a draft. So this one is more important, this formula is more important than the earlier one, because generally it will be written as ideal condition. Okay, so we have to use this one. I will talk about that one a little bit later. Okay, so next we will talk about the tube drawing. So wire drawing is completed. Tube drawing is basically here is a similar kind of similar to wire drawing. Only thing is that in the tube drawing, what is done, either you can actually the thickness of the tube, this is from here to here, this thickness is reduced to this thickness. Okay, this is h0 and this is h1. Okay, so the thickness of the tube is reduced. Now in some cases what happens, that even the diameter of the internal diameter, this is the internal diameter, right, from here to here, this diameter is also reduced in some cases. This is d0 and this is d1. So obviously the final diameter will also reduce. This is d0 and this is external diameter and d1. So die will be same as the wire drawing. Only thing is the mandrel is used. One mandrel will be there, which will be inserted from this side. Okay, so this mandrel is of two types. One is cylindrical mandrel and one is conical mandrel. So cylindrical mandrel, when is that cylindrical mandrel used? So cylindrical mandrel is used when this thickness is not required to be changed. Means this thickness, the internal diameter is not to be changed, right? Let's suppose that the object or the tube is having this internal diameter, and we want to keep this internal diameter same, but we want that its thickness is to be changed. Only the thickness will be changed, but internal diameter will not change. So in that case, we are going to use a mandrel which will have the shape, have cylindrical shape. Okay, so this is cylindrical mandrel. Right, and conical mandrel, when we want to change the internal diameter. So here is the internal diameter d0 and that has to be changed a smaller, that is d1, then we have to go for a conical mandrel. Okay, so now based on the movement of the mandrel, again mandrel is divided into two types. One is three types actually: a stationary mandrel, movable mandrel and floating mandrel. So a stationary mandrel, where the mandrel is fixed in one position. So due to that happens that when it is fixed, it is not moving with the tube. So there will be a sliding for friction here and here, because this is fixed and this one is moving. So there is a friction here. So at both the places there will be friction, mu1, mu2. So due to that, the drawing force, as we know, this one sigma 2 is equal to sigma by into 1 plus b by b, total b, right, into 1 minus that was h1 by h0. to the power b. Okay, where for a stationary mandrel b is equal to, earlier what was the b in case of wire drawing? B was mu by tan alpha. Here b will be mu1 minus mu2. Actually that will be mu1 plus mu2 divided by tan alpha minus tan gamma. Okay, where alpha is half of diangle and gamma is half of the conical angle. Half of the conical angle of mandrel, isn't it? Conical angle of mandrel. So when a conical mandrel is used, then gamma will be used. But as soon as we are going for a mandrel, in case of cylindrical mandrel, what will happen? Gamma is equal to 0. Put it there, right? So this is how the B is calculated in case of a stationary mandrel. What about movable? So movable, where it moves with the with the same velocity with the tube, so there is no friction, and since it is moving, so obviously this can only be which kind of mandrel, either conical or cylindrical, which one? So movable, since it is moving, so obviously it is going to pass through this one, right? So if it is conical, I think from here onward this cannot move in this direction, right? So that's why this only possibility movable mandrel is cylindrical mandrel. Cylindrical mandrel, and here in this case mu1 tan alpha, right? So the friction will be only one. Where is that friction? Look at this. See, actually the friction, oh, there is a mistake here. 1 second. This is wrong. Actually, look at this one. See here, there is this surface in contact, actually it is sliding. So this is mu1. The friction coefficient along this surface is mu1. Friction coefficient along this surface is mu2, right? But in case of a stationary mandrel, so when the mandrel is a stationary, so at both the surfaces there is a friction, so mu1 and mu2 both are added. But in case of a movable mandrel, mu1 is only applied, but because this is moving with the tube, so there is no mu2. So right, that's why here you can see mu1 by tan alpha. In case of floating mandrel, actually it moves backward and forward inside the tube. Okay, so this is also cylindrical one. Okay, and B will be equal to mu1 plus mu1 minus mu2, because it can move to and fro, and the friction will be always in the opposite direction of the movement. So minus mu2 tan alpha, and oh, this is okay, both the mu1 and mu2 will be in opposite direction, right? So tan alpha, tan beta will not be there, it is moving with the tube, so it can move in forward or backward direction. So drawing a stress, we have already seen what is drawing a stress. We have seen sigma 2 is equal to sigma y into 1 plus b upon b, right, into 1 minus h1 by h0 to the power b. So that is what, where b is equal to basically mu1 plus minus mu2. I told in which case mu1 plus and all those things, and this is what. So now let's take the ideal condition. What is the ideal condition? So B is equal to 0. That means mu1 is equal to mu2. Just take an ideal condition. Similarly, alpha, okay, this is 0, so obviously okay, so B is 0. So in that case, what will happen? Sigma 2 is equal to sigma y ln h. Now it will be reversed, so h naught by h1. So take this one. So this is the ideal condition. Okay, so we can use this one, this formula. So some of the limitations of drawing operation. So drawing operation, as I told that when we are using tensile force, so what is happening that there will be some portion which is elastic deformation, some portion will be plastic deformation. So load has to be applied for some more time to convert elastic deformation into plastic. That means the tube the die length will be much longer, and due to that the friction force is higher and power requirement will be high. Okay, so what is done that rather than it has been found we have flow stress sigma by, right? What is that flow stress? So you have seen this is sigma and this is epsilon. So sigma for the mild steel it is like this, if you see, but if the force or a stress is not tensile, it is compressive, that is minus sigma. अगर आप देखो ये तो मैंने पुल करके दिखाया था ना कि आपने पुल किया एंड आफ्टर दैट यू हैव लेफ्ट दैट एंड इट हैज कम टू इट्स ओरिजिनल शेप. बट व्हाट अबाउट द ऑब्जेक्ट व्हेन इट इज पुश्ड? So when it is pushed, the sigma is negative. So it has been found that the curve is like this, some kind of this one. Okay, and when it is coming back, there is no elastic deformation. Okay, so which has to be converted. That means we are completely getting what we are getting, only plastic deformation from here to here, plastic deformation. But here, as this one is coming back, it comes like this one. So there is some portion as plastic deformation and some portion elastic deformation. So that is not the case in case of compressive force, and that's to take that advantage extrusion was developed. That means to compress the metal rather than pulling the metal, what to do? Compress the metal. So that was the thing. As you can see, rather than this is pulled, what we are doing, we are pushing, we are applying force from the this side. Okay, so before going to, let us solve one problem of drawing operation. So here it is written 12.5 mm diameter rod is to be reduced to 10 mm. So obviously diameter rod, so d naught is equal to 12.5 mm, d1 is equal to 10 mm at a speed of 100 meter per minute. Velocity 100 meter per minute. Assuming the die angle is alpha or 2 alpha? 2 alpha is equal to 5 degrees. And coefficient of friction given mu is equal to 0.15 between the die and the steel rod. Okay, now he is asking about the power calculation. What will be the power? Okay, so and maximum possible reduction in the diameter, maximum possible when sigma 2 is equal to sigma y. Is sigma y written somewhere? If the rod is subjected to back pressure of 50 Newton per millimeter square, what would be the draw stress? Take yield stress of the work material. Okay, sigma y is given as 400 Newton per millimeter square. Okay, so the question is, we need to calculate drawing load. So can we take the ideal condition? No, there is no possibility of ideal condition because the friction is given coefficient, so we have to go for the complete sigma total we have to calculate, right? That means sigma 2 formula we have to use, that is sigma by into 1 plus b upon b into 1 minus what was that, final upon initial, to the power d, right? So we have to use this formula. B is equal to mu upon tan alpha. Mu is given, yes, tan alpha we will calculate. So that is generally 3.435. just calculate this one. Alpha is here, from here alpha is equal to 2.5 degree. Okay, b sigma by is kept in a1 is from here, d1 is given, so a1 will be pi d1 square divided by 4, a2 will be, sorry, a0 is equal to pi d0 square by 4. Clear? So just put it all the values in the sigma 2 and calculate sigma 2, that is 404.953 megapascal. Millimeter, isn't it? Okay, so megapascal. Now sigma 2 is calculated. Can we calculate force? Sigma 2 into load area 1, right? So a1 is this one, so just put it there and get it. So some value will come, that is around total power required, maximum possible reduction in the diameter of the rod. Okay, so we can calculate from here. Now power is equal to force into velocity. Force is given, okay, velocity is given 100 meter per minute. Take care of the units, right? So here if you just get some value, then that will be in some kilonewton or something like that. Just take care, because this is in millimeter here, so if you multiply then it will change it. And power, watt, power is, the unit of power is watt. What is the watt? Newton, that is Newton meter per second, that is watt. Okay, so if it is kilonewton meter per second, then it will be kilowatt. So just take care of this. Force has to, velocity has to be in meter per second, so convert it into meter per second. Where is that? Yeah, this is meter per minute, just divide it by 60 meter per second. Force converted into Newton, don't keep it in kilonewton, just convert it in, and then you will getting in watt. Now you can convert it in kilowatt, megawatt, whatever it is. So for maximum possible reduction, sigma 2 should be sigma by, okay, so back pressure is applied, some kind of back pressure is there, subjected to back pressure of 50 Newton. Okay, just leave this one, this portion I have not talked about that, so just leave it, because there is this expression will change. Okay, sigma 2 into something more will come, so that is not required right now. Just take it simple one, this much if you just go on, then it will go on increasing. So just I want to show you that how the problems will be solved. So in some question it will be asked, take it as ideal condition. What is the ideal condition? Coefficient of friction is 0. right? As soon as coefficient of friction is 0, then B is 0, and in that case sigma 2 will be sigma y into ln a naught by m. So it becomes much easier to calculate. Sigma 2 is calculated, a1 is there, so force will be calculated, and from there power can be calculated. Clear? Next topic, which is extrusion. So let us talk about that extrusion. As I have told, why extrusion is used, because it is beneficial as the compressive force during compression, there is no elastic deformation. That means complete deformation will be a plastic deformation. So that is the benefit of extrusion. Otherwise, it is also used for wire, wire production of the wire. Okay, so any amount of deformation is possible. Okay. So these are all not required. There are 4 types of extrusion: forward extrusion, backward extrusion, hydraulic extrusion, and impact extrusion. So this is forward extrusion, in which the direction in which the ram is moving and the direction in which the component or the finished product is coming, both are same. This direction and this direction is same. So what is happening, this material is basically moving, so there is a friction at this point and this point, right? There is a friction at this point, right? So this is known as forward extrusion. What is backward extrusion? So as you can see that this is the plunger, or this is the piston with which the force is applied on it, but in the piston only itself there is a small hole which is kept, and through this hole the material is flowing, because from the front there is no space to for the material to come out, so it will be coming from backward, in the backward direction, right? So the direction of the force which is applied on the ram and the direction of the product is opposite. Okay, and now why this backward extrusion is used, we will see. So as you can see that the material is moving from here, so this material is not moving anywhere, so there is no friction at this point, only friction observed is at these points, right? So the friction is reduced in backward extrusion. So that is the benefit of backward extrusion than forward extrusion. Now why this backward extrusion is used? So some of the materials are little bit brittle, okay, semi brittle, so these are little hard materials, and when you are going for extrusion, then there is a chances of cracks and all those things, forward extrusion, because there is a lot of friction force which is applied, and that is not good for the material. So that's why brittle material and semi brittle material is backward extruded. But the problem with the backward extrusion is, first of all, the area of the plunger or area of the ram is reduced. Are you getting? This much area only is applying force, so the force application will be limited. Second point is that it has to be put fixed centrally, because the force is very high, and if it is shifted somewhere here, then there is a chances that the piston will apply force more at this direction and less at this direction, or something like that will happen, and that is not good for the die. So in forward direction, forward extrusion, there is no such problem. You can put this hole here also, you can put here also, there is no problem in it. But in case of backward extrusion, it has to be centrally aligned, right? So that is the only disadvantage of backward extrusion. But because it is useful for brittle material, so that is okay, we can go for it. Now the point is that see, both have advantage and disadvantage. So what to do? So there was another extrusion method which was developed, that is that that uses the benefit of both the extrusions, and that is known as hydraulic extrusion. So how this is like using the benefit or advantages of both? First of all, it is forward. So there is no problem of centralizing this hole. Second thing is that since there was a friction, so what we have done, this object, the material which is extruded, actually the whole die is not filled with the material, rather uh, a smaller billet or a smaller material is used having less volume than the die, and rest of the part is filled with the liquid, some kind of liquid, hydrostatic liquid. Okay, so this liquid will apply force because the force is applied by the ram, and that will apply force, and that force is like, it's not in one direction, from one direction, it is hydrostatic force. So it is from all the directions which will apply, and that is very very good. So from one direction is not. Only problem with hydrostatic extrusion is, although it is very very nice process, the problem is because the force will be applied is very very high. So now you can understand there is a chances of leakage of this liquid, right? So there is a chances of leakage from here and from here, so leakage may happen. So that's why while designing this hydrostatic, you have to be very careful. So as you can understand that the hierarchy goes like this: forward extrusion, the die for the forward extrusion is less costly, right, than die for backward, but the maximum cost will be die for hydrostatic, because it has to be completely hydrostatic extrusion, it has to be completely insulated, no water can come out. Okay, so now there is last one, that is impact extrusion. What is impact extrusion? So here very thin wall tubes are prepared. As you can see, this material is deformed into this much big tube, and generally this tube is made up of very soft material. Okay, like toothpaste, you have seen, toothpaste tube. So this is made by impact extrusion. Okay, so in extrusion also the similar kind of forces are used, that is sigma extrusion, or sigma naught is equal to sigma by into 1 plus b upon b into 1 minus a1 by a naught, right, final by initial. Sigma naught is the extrusion stress, b is mu by tan alpha, right, alpha is the die angle, half of the die angle. Okay, so extrusion force in case of backward will be how much? In case of backward, it will be let's suppose this is the area. Where is that? Yeah, if this area is given, that the force which is applied, the area is given is a naught. Okay, just remove this part and then you have to calculate, that is area that is a naught. So if we put that one, then it will be sigma naught into a naught. But effective pressure in case of forward is sigma naught plus pt, that is the friction force, into a naught. So pf, so pf is friction force, pressure required overcoming container wall friction. Just write it, pressure, this is pressure, no, pressure into force is that, pressure into area is force. So pressure required for overcoming friction or wall friction, right? So force has been calculated. Can you tell me minimum force? So as I told, the minimum extrusion force will be if sigma naught is equal to sigma pi, that means sigma pi into a naught, right? So now sigma naught will be ln if we say the ideal condition, that is sigma pi into ln a naught by a1, same thing, right? So we can take one example also. In a direct extrusion process, this much length billet is and 50 is extruded, okay, length, and this one is given. Considering an ideal deformation, that is ideal deformation is happening, extrusion 4. Oh, what is extrusion ratio? So extrusion ratio is 4. We have seen draft was a naught by a1, that was there, no? Draft, do you remember that? What was the draft value here? Draft is a naught by a1. That is also the same in extrusion also, that is extrusion ratio, that is given is equal to 4. Average flow stress 300 megapascal. So the pressure on the ram will be, since it is direct around billet is to be extruded, that means a naught is given, isn't it? A naught is given 50 mm diameter, so so the pi by 4 into 50 square, that is a naught. So can we calculate a1? This is millimeter square, isn't it? So a1 can be calculated is equal to a naught. Oh, a naught is given, so 4 divided by a naught by 4, isn't it? A1 is equal to a naught by 4. So just to get this value, now extrusion force is equal to, so extrusion force is equal to sigma by ln a naught by a1. This is the stress into a naught. A naught is what? The initial, it is the extrusion process, isn't it? So we have to take this one, or the whole size. We cannot take this one, this is a1 and this is a naught, right? So we are not going to take a1 because the force is applied on this and this, isn't it? So that will be a naught calculated, isn't it? So just put all the values and we will get the value. Okay, so extrusion force has been we have got, and just so it is asked what the pressure. Oh, okay. So we don't need extrusion force, just divide it with a naught. Oh, this one is not required. Okay, so extrusion force pressure, that is extrusion pressure, calculate sigma by ln a naught by a1. Okay, so last topic, that is forging. We will talk about the forging and then we will finish our class. So forging is known as, it is almost the oldest metal working process. Okay, so this is basically what is done. The metal is heated up to a certain temperature, that is above recrystallization temperature, and after that plastic deformation is done by applying force. So there are two types of forging. One is known as open die forging and another one is closed die forging. What is open die forging and closed die forging? So in open die forging, this is the platform on which piece is kept, metallic piece will be kept here, right? And on this the pressure is applied. So by applying pressure the shape is changed. So this is known as open die forging. In this case, what is done? The shape is changed manually, or you can shape is manipulated or obtained manually. are you going to, whatever kind of shape you want, you can get it by applying pressure in certain directions, right? If you want to change it in this shape, you can change it. If you want to change it in this shape, you can change it, right? Any kind of shape you want, you can get it from this one. But closed die forging, where what is done, that this fixed one will have a certain shape, this is that, and metal is placed here, and the outer one will have also certain kind of shape. Let's suppose this is okay, and when this die, this is one die, this is another die, this is known as closed die forging. So what is happening, this will go inside and it will press this one, and it will get which kind of shape? So it will get this kind of shape. This is the final shape which we will be getting. Okay, so this will come down and you are going to get this kind of shape. This is the final one. Clear now? So that is closed die forging. So here the shape cannot be, any kind of shape cannot be obtained. The shape which is given here, like the die is made up of having the same similar kind of shape, so that shape only you are going to get it. But in case of open die, you are going to get any kind of shape. But the problem is with the open die is it is slow process, as you can see, and second one is that the dimensional accuracy will not be good. As you can see, if you want this diameter 20, you may not get 20. But in case of closed die forging, first of all, it is fast process. Second, the dimension will be accurate, completely accurate. Third, the surface finish will be very, very nice. And fourth condition is that actually closed die forging is never done by hand, right? Manually you cannot do. Here it is manually open die forging, but it is not done manually, it is done by machines. Okay, so based on that, there are two types of forging. One is machine forging and hand forging. Machine forging and hand forging. So as you can see, this is a movable die and this is a stationary die, so it is actually open die forging, because as you can see, there is no kind of closed die used, right? So because it is an incompressible material, so can we write pi by 4 d naught a square, initial diameter is d naught, has been changed to df, initial height is h naught, has been changed to hf. As it is moving down, so this will be h naught is equal to pi by 4 d square hf, right? So from here, whatever you want, you can calculate. If three of them are given, you can calculate df. So hand forging and machine forging, as I have told, hand forging manually done with the help of hammers, okay, drop hammers. Machine forging is done by either mechanical forces are applied or hydrostatic forces are applied. So any kind of things you can use. Open die, closed die, and semi closed die. Semi closed die is also one method in which what is done, this is fixed and there is a metal and there is a see the blow which is done, that will have a shape, right? So by let's suppose this is that, so by applying this intermittent, actually this is also done intermittently, मतलब ये बार बार आपको इसी के थ्रू आप जो है ना, सॉरी रॉन्ग, हाँ, closed die for sorry, semi closed die forging. So what is semi closed die forging? Let's suppose you have a rod, metallic rod, something like this. You want a hexagonal head. You have seen nuts and bolts, so that will have this kind of shape and there is a rod, so this has to be changed in this way. We want that one. So how to get this shape? So there will be a die which will be used like this one, and here the metal will be put hammered. with the help of hammer. The force will be applied. So when the force is applied, it will slowly get the shape of this one. So it's a semi-closed die forging, right? So here what is happening, although there is a shape on one die, but this is not completely closed, because here the manual forces are applied, and you have to rotate this one, okay? But in case of closed die, completely it is done by machines, and there is no chance that you can change the shape. Whatever shape you want, you can get. See, actually from here you can get any kind of shape. Either you can get hexagonal, or you can get this kind of shape. So you can get it from here. Hand forging, machine forging, open die forging features: repeated blows are required. Dimensional accuracy, as I have told, it is not. It is only used for simple shapes. Require more skills. Okay, yeah, simply you cannot do, you cannot get exact, almost. Even when you are doing forging first time, you will see that open die forging basically, then you will see that you are not able to get even close to the dimensions which you wanted. That is not good, but it is a little bit less expensive, okay? And it is good for analyzation, what kind of forces and how much, all those things are easy for this one. But in case of closed die forging, this is also known as impression die forging. So in the examination they may ask this term, impression die forging, what is that? So don't tell me that, sir, I haven't heard about this. Yes, actually it is a closed die forging. So here we are doing, the force applied is not by hammers, okay? It is generally done by press forging, okay? So we can get complex shape, but it is expensive. In case of semi closed, it is not so expensive, and also we are going to get a good surface, or you can say good shape, we are going to get. So in case of closed die forging, as you can see, there is a gutter is provided. Why this gutter is provided? Because in case of closed die forging, we provide extra materials. Why? Because if extra material is not provided, there is a chance that whole space in the die will not be filled. There is a chance, isn't it? So what we do, we'll give little bit extra material. Now that extra material obviously it will exceed the size or volume of the die. So when it is exceeding the volume of the die, obviously the extra material has to be flow somewhere. So for that, gutter is provided, right? Extra space is provided, so there it will be collected. Now once the forging is done, after that you take out the casting and remove these gutters, right? So you might have observed that when the forging is done, let's suppose I want to make a ball, and you will find that just like on the ball, there will be some kind of thin at the middle, it will be found. So this has to be removed, right? So this is known as flash. So that has to be removed. So you understood what is the purpose of gutter and flash. Now the forces which are applied in the forging operation basically is nothing but so it's since, as you can see here, so just to go there, this one, yeah, here. So just I'll put it here. So in the beginning the diameter is d naught, right? So there will be cross sectional area, that is a naught. So in the beginning there is a force, initial force, minimum initial force which is required is, because see, after sigma by going to deform, so this is the minimum force which is required, that is sigma by we have to provide, isn't it? Sigma by into a naught. But final force, that is minimum, that is sigma by into a f, right? So the average will be the average force which we will apply, that is this much by 2, okay? And if we find out actual force, F actual, then little bit complicated formula is there, that is not so much required. This kind of equation, numericals will not be asked, as in this examination objective questions will be asked mostly. So there is no requirement of paying much attention on this. But energy or work done, that we can calculate, isn't it? So work done is equal to F actual into H naught minus HF. That is the change in the height, that much force. F actual is the basically average force basically. So F actual is into change in the displacement, or whatever you can say, change in height. So that will give you work done. Okay, so I think we have completed our talks, and one question is given. A strip of lead with initial dimensions are given. This is cross sectional area into height, force between two flat dies to a final dimension. This is the final dimension. Okay, this is 150. Oh, right. Okay, so the complete length is not changed, so 24 into 24 is changed to 6 into 96. That means which one is diameter and which one is H naught? Can you tell? So H is reduced. So H is reduced. This one is H. Okay. And this is D. D is increased. If the coefficient of friction is this one, so mu is given. Determine the maximum forging force. The average yield stress has been given. Sigma y is equal to 7 Newton per millimeter square. Okay, so height. Oh, acha. This is not diameter, because it is a three-dimensional, no? So it's maybe something cubical kind of thing, not sorry, cuboidal. Okay, so if we see this is height H naught, look at this one, and if this is height, so obviously there will be one dimension, that is 150, and there is another one 24, and this is 24, that is H naught, and that has to be changed. So height is reduced, this one is increased, but this length is not changed. That means this is 150, this is 96, and this is 4. No, 6. This is 6, right? Okay, so that means cross-sectional area, the force is applied on this area, that is 96 into 150, or here the force is applied on 24 into 150. Okay, so that means A naught is 24 into 150, and AF is 96 into 150, and H naught and H1 is given, or HF is given. HF is equal to this much. Okay, so sigma y is given. Okay, so we have to use this formula. Okay, so this formula where RF, basically RF is equivalent radius. Equivalent radius. So we have to calculate equivalent radius. Means this cross-sectional area, let's suppose it is of 150 and 24, isn't it? So this has to be equivalent to some radius, isn't it? Ri or Rf, something. So convert it into that one. So I think that is not required. So just we have to put the formula and we have to get it. So we will not solve this problem. So just understand that what kind of problem is possible, but only the point is that to remember these terms, they will be asking these terms in the objective. Now this is very important, the forging defects. This is the last topic, because from here the question will be asked. Unfilled section, as I have told, why this unfilled section happens, because let's suppose this is the a space and you have used this much material only. So this is the unfilled section. So if you have used and you compressed it and it has been found that this has filled up to here but this space is left, so that is unfilled section. So this is because of the improper design of that or forging die, or there is a chance that like while forging you have done something that some material is wasted, है ना, आपने लिया तो material लेकिन क्या हो गया, कुछ material it is wasted. So that is due to means faulty forging technique. So cold set, what will happen, that there is, let's suppose we are doing forging and there is some space in the die which is having very small area. Okay, so what will happen, the whole thing will be filled, right, but this zone is left. So this is known as cold set. It's similar to unfilled section, but it's because of the very thin sections which are not approachable. A scale pits, this is because of the uncleaned surface. There will be a scales sticking on the surface, and when you are forging, then that will be remaining there as a pit, because when they will be removed, then they will form something like this kind of pits. Okay, here the scale was there and that has been removed after forging, so that kind of impression will be formed. Die shift, so if two dies are there, one die and there is another die and they are not properly aligned, so due to that die shift problem will be happening, right? Like I wanted to make a ball, metallic ball, okay, you are getting this kind of ball, so is it good? So this is known as die shift. Flex, so internal ruptures which is caused, flex are basically internal ruptures which are caused by improper cooling of the large forging. So this is because of the rapid cooling. Okay, so due to that surface is getting cooled fast, but inside it is little hot and it is slowly cooling, so there obviously there will be a tension that will arise, and due to that crack will happen. So simple, you do proper cooling, you will not get flex. Improper grain flow, yeah, we have talked about the grains, right? And you know that forging is basically used to increase the strength by aligning the grains in a direction, and if the grains are not properly aligned, then that is the problem with the forging, and that we don't want, right? So we have to make sure, like if we are making a railway wheel, right, this is the railway wheel and the grains are not properly aligned, the grains are all in this direction, is it good? Not good, because it has to be radially oriented, right? So that is not good. So here we have completed our forging, all the complete bulk metal forming. In next class we will talk about sheet metal forming, that is a small portion, and after that we will talk a little bit about powder metallurgy. So maybe tomorrow I will cover, I'll see, tomorrow I'll give you the video for forming and powder metallurgy, and that's how our syllabus will be completed. Thank you very much.